Yeah. Okay. So a very good morning, everyone. So welcome to our webinar today. Before that, let me first introduce myself. I'm Dr. Moon Wei Chek from the Faculty of Engineering and Built Environment, Masa University. So nowadays, actually, CFD has become a quite important tool in engineering design and also planning because we have the rapid increase of the computational power and also our affordability of the desktop computer. Therefore, the content of the webinar today will focus on CFD, or we call the computational fluid dynamics. So in this webinar, a general introduction will be first given to the application of CFD model for the simulation with the free surface, and then we will follow by the fundamental concept, the advantages and the disadvantages of the model, and then the differences between the models also. So before that, let me introduce our speaker today, Dr. Pui Hao Tian from the River Engineering and Urban Drainage Research Center, REDAC, in University Science Malaysia, USM. So actually, Dr. Pui is my mentor during my postgrad study. So in Chinese, we call this as a sifu lah, sifu. So my sifu, Dr. Pui, was awarded his PhD title from the Kyoto University for his analytical and also numerical models in open channel flow. So currently, he is actively developing and improving some models for the tsunami wave interaction with the coastal structure and also some mud flow phenomenon and the sustainable drainage system. So without further ado, let me welcome Dr. Pui to present his talk on the simulation of free surface flow with computational fluid dynamics CFD model. So thank you very much, Dr. Pui. You can start when you are ready. So I will quit the sharing first. Okay.
Okay, I'm ready.
Okay.
How can I
So
start?
you can start.
Can you
Yeah,
see
yeah,
the
you
screen?
can start. Not yet.
How about now?
Yeah, I can see the screen. Yeah,
So, so can I start now?
yeah, you can start now, Dr. Pui.
Okay, thank you, Dr. Moon, for inviting me to this online webinar. The title of my presentation today is Simulation of Free Surface Flow with Computational Fluid Dynamics CFD Model. So this is the layout of my presentation today. I will start with a short introduction to CFD, and then in the second part, I will introduce to you free surface flow model, the definition and application, as well as their governing equations. And then we will dive into the classification of free surface flow model. Basically, I will touch only on the characteristics of the model, their advantages and disadvantages. And finally, some tips to set up a CFD model, some basic tips from my experience. So what is CFD? Dr. Moon has just explained. Given he has given the definition of CFD. So CFD is actually a fluid dynamics. Computational fluid dynamics is a branch of fluid mechanics that uses numerical analysis to analyze and solve problems that involve fluid flows. Because it involves numerical analysis, a lot of iteration calculation has to be performed, and therefore a computer is an indispensable tool to complete or to carry out the calculations in CFD. You can see here this is an old photo of a computer. So it is as large as a room, but now computer has advanced so much that we can bring computer every day in our pocket. Yeah, our handphone is a kind of computer. So with the advancement of a computer, especially in terms of
Totally, sorry, so sorry for interrupting. But
yes,
you have, yeah, yeah, because just now the slide is not moving. Yeah,
how about
now,
now? It is
now
moving.
yes, now it's in the computing cost. Yeah, yeah,
Yeah, okay, maybe because of the lag in internet speed.
yeah, yeah.
So, okay, with the decrease of average transistor price, so computer become more affordable nowadays, and also the speed of computer has increased exponentially. So this means computer can be effective tool in terms of cost and in terms of speed to help us in engineering design by using CFD. So in the market, you can find a lot of proprietary software such as Flow Science, ANSYS Fluid. OpenFOAM is a free software, so as well as HackRAS. But Might by DHI is not a free software. So you can find various types of computational fluid dynamics in the market. Evolution of CFD. So in the first generation of CFD, computer is used to calculate numerical values from formulas. Then in the second generation, it involves coding and model testing by solving simple variation in time and space with finite difference method. And normally, these models are dedicated custom-built models. Then it evolves into the third generation where modeling system that construct and run any models when description is given in specified format. So a modeler can give description to the model in a specified format, such as in Flow 3D and ANSYS. And then in the fourth generation, model can be operated by a non-modeler. So it comes with menu, help facility, default values of parameters so that any inexperienced operator could provide adequate accuracy. So the system is menu driven and fault tolerant. So for example, GPS uses the ICM Live in the National Flood Forecasting and Warning System. So in this fourth generation also, a hydrodynamic model can be added, such as gate control structure, then break flood, forecasting, and so on. And then comes the hydroinformatic terms introduced by Abbott in 1991, where real-time control and diagnosis can be carried out. And normally, this system is superimposed with this a SCADA system. And recently, the term digital twin is born, and it basically is a term used to represent a virtual representation of a physical process or object which serve as a real-time digital counterpart. So it is also known as a device shadow. Basically, we replicate the model or the system in digital form, and then we use real-time computer data to create simulations to predict uh, to predict how the process, how the system will perform. So it can be integrated with IoT 4.0, artificial intelligence, and software analytics. So for today, I will just focus on the flow with free surface, the modeling of flow with free surface. So first of all, what is free surface? You can see from this picture here. So
Yeah,
very clear.
totally. Sorry for interrupt again because
Yeah.
got some audience they asking about the slide is moving or not. Or
Uh, the slide is
maybe total,
moving now.
yeah, or total can click for the slide show for the slide. Can play the animation.
Okay, can you see evolution of CFD?
Yeah, now can.
How
uh,
about flow with free surface now?
yeah, can. Yeah, now the line
So
is moved.
I think when I do full screen, the screen refuse to move, right?
Oh, I see. Yeah, yeah, yeah. Yeah, the screen.
Okay, if I do non-full screen like this, I think you can see the transition of the screen. Am I right?
Yeah, yeah, yeah. Yeah, yeah. Correct.
Okay,
Yeah.
then I'll leave it in this
No.
form.
Okay. Can also.
Okay, I'll leave it in
Yeah.
this form without going full screen. Is it okay?
Yeah. Can sure. Okay.
Okay,
So Dr. Hui, you
back
can
to the.
proceed.
Can I continue?
Yeah, yeah. You may proceed.
Okay, so what is free surface? Free surface is the boundary between two homogeneous fluid. For example, between air and water here. The characteristics of free surface is it is always subjected to normal and tangential stresses. Surface tension force exists on the surface, and surface can break and combine in the case of a violent flow. And to simulate free surface, it is quite difficult and very challenging because surface configuration keep on changing in the case of unsteady flow, and it can also break. Yeah, the surface can break and combine. Therefore, not all model can simulate free surface due to the very costly and complicated process of representing free surface. So different types of free surface tracking methods are being introduced, and these free surface tracking methods always affect the accuracy of the model. So a lot of research will carry out and still being carried out to improve these free surface tracking method and to improve the accuracy of the model. Of course, due to the free surface tracking methods, it always affect the computational cost. So the most common free surface tracking method, can you see my slide now? New slide?
Yeah, can. Open channel flow. Yeah.
Yeah, okay. So the most common free surface flow phenomena in our life is open channel flow. So open channel flow is a special case where the free surface flow is subjected to atmospheric pressure on its surface. Yeah, for example, here, uh, the pressure is atmospheric pressure. So we call it open channel flow here. So the most common one is river. We can see river uh, everywhere in Malaysia. So this is a type of open channel flow. I'll show you some application of CFD in open channel flow. For example, this is a video. Can you see the video now?
Yes.
I'm playing a video of the release of water into a spillway. Dr. Moon, can you see the
Yeah.
video?
Yes, yes. I can see the video.
So in the release of water into a spillway, after some time, the water will become steady and become supercritical, and it will hit the sidewall here. Can you see the sidewall on the left and right hand side of the spillway? So this is the initial condition, but after some time, the flow will develop into a supercritical flow like this. This is the second slide. Can you see the second slide, Dr. Moon?
Second slide.
Still in the video,
This
right?
one's still the
Okay,
video of the spillway.
okay,
This one. Yeah, yeah. I can see.
okay.
I can see
So
already.
there's some problem. So after some time, the flow will develop into supercritical flow, and shock wave will be generated, oblique shock wave, and this shock wave will hit the sidewall here. And the point where the shock wave hit the sidewall is called the impingement point, and it is very important to determine this location so that we can reinforce the wall at this location, and we can save money by not reinforcing the whole stretch of the wall, but by reinforcing a certain part of the wall only. So there, this is where CFD play a role, where you can investigate based on the inflow condition, based on the fruit number of the inflow, you can predict the location of the impingement point. Therefore, you can reinforce your sidewall here. So uh, my group or my students that develop in USM, we develop models, 3D model using some method. This is the VSIAM 3 method to simulate this kind of phenomena, the sudden expansion phenomena. So you can see for fruit number two, the impingement point is somewhere here. Yeah. And if we increase the fruit number to fruit number four, you can compare with the fruit number two. It's slightly downstream. Yeah, slightly downstream here. So by using this model, we can predict and we can reproduce the shock wave and the impingement point can be known before construction. So you can also use, the video cannot play simultaneously. You can also use Flow 3D, which is a proprietary software, to investigate the release of flow through a jet gate here. Okay, so this is by using a proprietary software. Another example in the dam is the water intake phenomena from a tower in a dam. Yeah, so water is we do water intake through a tower like this, but there are several things that can be studied using CFD in this water intake process. So by using CFD, so we can predict the phenomena of gate opening at the water tower intake. So water will enter the intake, will enter the pipe here through the emergency gate, and you can see here when the water enters the pipe, the water will shoot up in the air vent here. Yeah. So this is when the gate opening is 25 mm. However, if we open the gate slowly at 10 mm per second, you will see that the water doesn't shoot up the air vent as high as in this case, in the initial case. So if we open it at 10 mm per second, you can see that the water didn't shoot up very high in the air vent here. So we can use CFD to predict this kind of phenomena to avoid any accident on site when you open the emergency gate at the intake tower. So you can see that the water didn't shoot up very high as compared to this. Yeah, to the left hand side where the gate is open at 25 mm. So this is one of the application of CFD in water intake tower. We can also use the same model to see if the gate can close by itself under its own weight. Yeah, due to the hydrodynamic force underneath the gate, it is sometimes difficult to close the gate under its own self weight. So we have to make sure that the gate can close under its self weight. If not, then we have to do something mechanically to ensure that the gate can be closed. So we can use CFD to investigate this phenomena. So CFD can also be used to study flood. So this is a real case in Sungai Jarak, Kedah. So where we simulated, this is by using proprietary software. It's called ICM. So we can see the extent of the flood and the depth of the inundation. Yeah. So I only focus on this part. You can see that the water is inundating the area on the left hand bank, at the left bank, and also the right bank of the river. So we can use CFD to study this inundation phenomena. So finally, by using that model, we can come out with what we call a flood hazard map. Yeah, this is a flood risk map for Sungai Perai in Penang near Butterworth. Yeah, so Perai has a lot of industrial activity and also highly populated at the downstream. So it is important to know the risk of flooding along Sungai Perai here. So we came up with this hazard map by using ICM model. So after showing you several applications of CFD in free surface modeling, I would like to introduce the classification of free surface model. So normally to carry out free surface modeling, we use a full 3D model. This is a full 3D model where the 3D continuity and momentum equations are solved. This is the continuity and momentum equations. I will not dive into these equations here. You can find it in textbooks. So by solving the continuity and momentum equation, we can define at all point in the domain. For example, this is a dam break. Oops. Uh, can you see the animation of the dam break here? Dr. Moon, can you see the animation?
Yes, I can see the simulation.
Okay. So by using a 3D full 3D model, the pressure and velocity at any point in the domain can be known. Yeah, and the fluid velocity, the fluid configuration is updated based on the calculated velocity. So the application, where do we use this 3D model? We use it in a three-dimensional problem. Okay, if you need to know the configuration in 3D, then you have to use a 3D model. So, and also in cases where the free surface is changing very rapidly with space and time, for example, in tsunami and also in sloshing tank, so we need to use this kind of model. Yeah, because the hydrostatic pressure is not, the pressure is not hydrostatic in this kind of phenomena, so we cannot use, it is more accurate to use a 3D model. So in the market, you can find these 3D model from Flow 3D, ANSYS Fluent, Autodesk, and for the open source one, you can use OpenFOAM here. So in this case, we are using, in this animation, we are using volume of fluid method as a surface tracking method. So based on that model, Dr. Moon developed a tsunami model to study the impact of hydrodynamic forces on the surface of a building here. So you can see that this is on the top side. It is the model developed by Dr. Moon, and at the bottom, you can see the result from Flow 3D. So comparatively, you can see that the resolution of the model developed by Dr. Moon is more accurate. You can see more resolution. You can see that the surface of the wave is more detailed compared to the one in Flow 3D here. This is because in Flow 3D, the maximum degree of accuracy in the advection scheme is only up to second order. While in this case, in Dr. Moon's model, we use a third order advection scheme. So how do we know that our model is good? We can actually validate it with experiment. You can see in this slide here, we have experimental result on the left hand side, the first column. We have the developed model on the second column, and the result from Flow 3D at the third column here. So very obvious that the developed model has a higher accuracy because it is more alike to the experimental result compared to the Flow 3D one. And by using that model, you can change the inflow condition. So this is for 40 mm with height. This is 100 mm with height. You can see you can play around with the model with various inflow condition, and also you can change the shape of the obstacle here. So the bottom one is inundated, totally inundated. The obstacle is totally inundated by the wave height of 100 mm. So more importantly, if a model is developed, there is a need to check, to verify and validate the model. And one way is by checking the pressure. This is the pressure impingement at the impingement phase on the obstacle phase here. So you can see that the developed model is well verified here. Yeah, the dotted line is the experimental result. So the model agrees with the observation from the experimental result. So the benefit of using CFD is that you can always change the condition. Yeah, simulation condition, the obstacle shape, and so on. In this case, the model is used to investigate the effect of the roof shape. This is a gable roof. So by changing different shape of roof, it will affect the hydrodynamic force on the surface of the building here. So if you change the shape of the roof, you might reduce the hydrodynamic force. So therefore, your building will not succumb to high hydrodynamic force during tsunami. And also, CFD gives you a lot of flexibility because you can view from different perspectives. You can see the velocity vector around the building, how the flow develop, how the pressure is being distributed around the building. Okay, it gives you a lot of detailed view. This is another view here. Yeah, you can see how the flow develop at the back of the building here, as well as at the front here. So in another application, we use a 3D model to simulate flow over artificial reef structure. So this reef structure, artificial one, they are being installed in the river together with a rock ram here. So when flow is introduced in the channel, you will see that uh, at the downstream of the rock ram, severe erosion occur. Okay, as well as the downstream of the ship pile here. This is a ship pile installed at the downstream. So this is a replication of the phenomena of the situation in one of the river in Malaysia here, where a test is being carried out, where they are trying to rehabilitate the river by using artificial riffles. So the rock ramp is being installed here, and you can see underneath the water there are some concrete block, which is the artificial riffles here. Maybe in this photo you can see a little bit hard to tell, but there are some concrete structure underneath the water here. So we replicate these phenomena with CFD, and at the downstream of this river, they installed ship piles. So we use the CFD model to investigate the effect of the ship pile. So you can see that actually the ship pile causes quite severe erosion at the downstream. So some measure has to be taken at the downstream of the ship pile to avoid this problem. So next is the 2D model, because 3D model is too expensive in terms of calculation cost and time. So sometimes we can choose to use 2D model. So 2D model is much cheaper than the 3D models. It can be used where in phenomena where flow in one direction is negligible. Yeah, the rest of the characteristics are same with 3D model, just that if the phenomena can be represented by a 3D problem, then 3D model is more efficient. So this is a simulation of dam break flow by using a 2D model, but this time it is using marker and cell method. marker and cell method is one of the earliest methods for surface tracking. So there's an obstacle here. So you can see that the flow surface is changing at all time. This is another comparison between an experiment of dam break flow with the model developed. So we use marker and cell here. You can see the comparison between between the experiment and also the numerical model. This is a 2D model, and the experiment, of course, is a 3D phenomena. So this tells us that a 2D model is not as bad. So if the phenomena can be represented by a 2D model, uh, we can choose 2D model, yeah, to save cost, to save calculation cost and time. So with that, we can apply the model, for example, in flow in porous media. So nowadays, there are some ideas to store water underneath the road. Yeah, this is a road pavement. Some road pavement are made porous, and some has a side drain where the water runoff will be stored, will be channeled into the side drain, and then channeled to the a compartment underneath the road. And this compartment is made of porous media such as aggregate. So we can use numerical models to study whether the selection of our aggregate is suitable or not. And we can also investigate the time for the water to intrude laterally into this compartment here. So this is an experiment carried out. This is not carried out by me, but by some other researcher, but we developed a model to compare with this result here. Also, we can use the model to study how the flow will infiltrate from the top surface. Yeah. So the yellow color here is a porous zone. So we release water and we can see how well the model perform in terms of water infiltrating through the surface of porous media. So you still remember the serious flood in Sungai Klang, because some rumors said that the tidal gate was not open during the uh, heavy rain, so it causes severe inundation in Klang area. So this is a simulation of a sluice gate, the opening of a sluice gate with erosion. Yeah. So normally sluice gate can be used to prevent high tide effect. So this is at the downstream and this is at the upstream. You can see when the gate is open, severe erosion will occur here with deposition. So some measure has to be taken at the downstream of this site here. Yeah. So we can use a 2D model and it is adequate. A 2D model is adequate for us to come up with some meaningful result. So we don't necessarily have to resort to 3D model, which is very expensive. And then the even cheaper model, cheaper means faster calculation, is the depth average model. So in depth average model is much cheaper and faster than 2D model or 3D full 3D model. So in this case, if we want to use this model, there are certain assumptions that we have to take into account, that we have to understand. In this model, vertical acceleration is negligible compared to acceleration in other direction. This means that pressure is hydrostatic. Yeah, it's been assumed as hydrostatic. So if the problem has vertical jump, so this model is not suitable. This model is suitable only if the vertical acceleration is negligible. So you can find this model in a lot of uh, flood model, such as in InfoWork, in Mine, in ICM, and so on, because they are fast and very cost efficient. So this is the model, how this model looks like. The governing equation, the continuity and momentum equation has been integrated vertically. So you have the average velocity and the average uh, parameter here. And pressure has been assumed as hydrostatic in this term here. So this is the assumption in that average model. The horizontal wave length is much larger than the flow depth. And we also have the 1D model. Yeah, previously I showed you the 2D, the average. We also have the 1D model, which is quite useful as well. And this is the simplest one. It is also known as the Sandanian equation. Next, I will show you some application of that average model. So in the first few slides, I show you the sudden expansion, the release of water from into a spillway. The same phenomena can be replicated by using a that average model like this. So this is much faster than using the 3D model, but some of the phenomena cannot be replicated. But the important feature that we want to see, such as the impingement point, the angle of expansion, can be reproduced well in this 2D model. So it is sometimes adequate to use 2D model. And also it can be used for other phenomena other than water. This is for mud flow. Mud, for your information, mud is not a Newtonian fluid. Mud flow is not Newtonian fluid. So we can use that average model to simulate non-Newtonian fluid. In this case, this is a release of mud flow from a reservoir and other kind of non-Newtonian material. So this is viscoplastic fluid from a reservoir. So maybe it's not so common to know to hear the terms tailing dam in Malaysia, but there's a serious disaster in Brazil where the tailing dam collapsed. In this tailing dam, they stored some the remaining of mining material mixed with water, so it become a non-Newtonian fluid. So it causes 270 deaths. You can maybe you can play some video to let you see. It was recorded live. This is the failure of a tailing dam. So it cannot be simulated by if we assume the fluid as water. So because this is a mixture of iron and water and other material, so it will flow as a non-Newtonian fluid here. Also, previously I've shown you some flood simulation. So flood simulation like this kind of model by ICM is also utilizing a 2D model. Yeah. So because it is not useful to use a full 3D model, a 2D model is more useful because it is fast and it can give you adequate information on the flooding. So there's no need to use a 3D model. And more importantly, during flood, the vertical acceleration, vertical motion is negligible compared to the spreading in the plane direction. How about the 1D model? This is a 1D model of a dam break. It looks very different from the 2D model because we don't see much of a real, it doesn't look realistic, but it is somehow useful in some cases. For example, we look at the simulation of hydraulic jump. This is a simulation of hydraulic jump. You can see there's a sudden jump of water here. So this phenomena is can be seen at the downstream of a spillway. And we don't need to resort to 3D model, 2D, even 2D model. We can use a 1D model to investigate the location of and the height of the hydraulic jump by using a 1D model here. So this is a replication of a phenomena like this. So such complicated phenomena is adequately can be adequately reproduced by a 1D model like this one. So this is the uh, reproduction of the hydraulic jump by using a 1D model. So that is to say, although the 1D model is very simple and not very realistic, but it can produce some meaningful and useful data, useful result for engineering application. And one important application of a 1D model is the simulation of flow in river. Yeah, because river is such a complicated system, but in a bigger picture, these flow in the river can be represented by a 1D model here, and the result from the 1D model can be fed into a 2D model, and it will be used for the 2D model to simulate the spreading of flood at the floodplain here, and then we can produce something like a, a hazard map here. So this is actually a combination of a 1D model and a 2D model. So the last part is the important points in setting up a model. So before we set up a model, we have to understand the problem that we are dealing with, what kind of data we wish to obtain from the model, what kind of phenomena we wish to see from the problem, and what is the scale of simulation. And then from there, we choose the correct model. First of all, we need to understand what the model can do. Yeah, we choose, can the model we choose reproduce the phenomena we wish to see or the data we wish to obtain from the model? We have to know this. And what is the simulation size of the model? And what kind of data the model require to reproduce the phenomena that we want to see? Another important point is we need to know the assumption that the model made. From all kind of models, they have a certain type of assumption. So we have to understand the assumption before we use the model. And we also know the model limitation, what it can and what it can't do. The fourth point is, to what extent do we need to replicate the actual site? Sometimes we don't need to exactly replicate the system, yeah, because we only need to know some important uh, parameter or variable that we want to know. So we need to know what extent do we need to replicate the actual site. Can we neglect or assume something, or will it affect the phenomena that we want to see if we do a certain kind of assumption? And the data that we can obtain determines the replicability of the actual site also. Finally, we determine the accuracy that we want. If we choose a higher accuracy, it might be numerically less stable, so we might have problem when we run the model, but of course it will give you very accurate result. For example, here we have animation of the third order and the first order. The third order one, you can see that the height of uh, the scala property is being conserved when it is being vectored around in a circular motion. Whereas in the first order, you can see that this is a lower order scheme. The height of the scala property is being diffused. You can see here. So lower accuracy means less accurate, but the advantages of lower accuracy model is it is very stable. And finally, how much time do we have? Do we have time to wait for long simulation? And also the cost. Of course, time is money. So we need to judge all these before we choose the suitable model. And my personal tips is always do from small, start out from the smallest part, and then add in other important part in stages. And also you can try with a coarser a mesh, and then you can increase the accuracy by reducing the mesh and perform mesh conversion tests. So this is a mesh conversion test. We can see that we change the mesh size, and we will see whether is there any good improvement if we change the size to a mesh size to a smaller one. So we can also do mesh refining in certain area that we would like to see more details. For example, here using non-uniform mesh size, we can select the area that we want to have more details. And finally, set the correct boundary condition. Yeah. So for subcritical flow, upstream boundary condition is certainly required. And for subcritical flow, a downstream boundary condition is required. So other kind of phenomena, we can use it Other kind of CFD application, for example, application of CFD in the simulation of fresh concrete here by using DEM model. This is slightly different. This is a DEM model, discrete element model. You can see the slump flow can be simulated. And also using DEM model, you can see we can simulate the arrangement of object. Yeah. So if you arrange like this, it might fail because it depends on the friction between all these rod here. So same method DM used in Flow 3D. This is for the compaction of particles for laser powder bed diffusion process. So that's all for from me today. I hope you enjoy and thank you for your time. Then I
Okay.
will, Dr. Moon, can I
Yeah,
pass
yeah.
the session to you, the floor to you?
Okay. Okay, sure, sure. So thank you very much, Dr. Pui, for your time to present in the webinar today. So it's quite interesting to see a lot of animation and also informative ifs and informative talk to learn about the application of uh, various type of the CFD model. So actually, it's undeniable that the CFD play an important role in the engineering today. Of course, we conducting the experiment is very time consuming, and we also require a lot of manpower. That's why we can opt for the CFD to reproduce and to estimate some flow parameter. Of course, when we saying that the estimation, right, is not 100% accurate, that's why we still need to do some calibration or verification of the model with the experimental result and also with their another CFD model. So before we end our section, let me see is there any question from the audience. So far there is no question, but we received some compliment from the audience. It's a great
Thank
sharing
you.
session from the CFD's knowledge, especially in the dynamic simulation prediction.
Thank you.
Okay, so before that, share. Uh, I'd like to share. I would like to share a slide of the certificate. Can you see it, Dr. Pui? Yeah. Can
Yeah,
you?
thank
Yeah,
you.
this is a certificate. So later on, I will send the PDF to you of this
Okay,
certificate.
thank you very much.
Yeah,
Yeah,
yeah.
thank you.
So yeah, before we end our section, of course, for those who are interested in CFD, you can contact Dr. Pui personally. And also for those who would like to become his master or PhD student, you are also welcome to contact him. And also for those who plan to do collaboration with Dr. Pui, you are also very, very welcome to contact him. Okay,
Thank
so
you.
it's very important, so I have to say 3 times. Okay, so yeah, actually, very thank you, Dr. Pui, for accepting the invitation of my
Mm.
invitation to
Thank
this
you for your
webinar.
invitation too.
Yeah,
And
yeah.
thank you
So
for thank you the participants.
what is it? So later on I will treat Dr. Pui for a lunch lah. But not
No, no
today, of
worry.
course. Yeah.
No
But
worry.
of course, not today because today Dr. Pui can eat at your side and I will eat at here.
Okay.
So we see you in the future if we have chance, okay, to learn more about CFD. Okay.
Yeah,
So
thank
Dr.
you
Pui,
for the
yeah,
session.
yeah. So do you want to add on something, Dr. Pui? Uh,
Uh, yeah, for those who are interested in CFD, I'm looking forward to do a research with you. So please contact me.
okay,
Please do not hesitate to contact me. So
okay.
I'm more
And
into developing in-house code, 3D model, tsunami model, mud flow model, and some other models such as DEM. So if you're interested, you can to do your master or PhD or whatsoever, you can always contact me. Thank you.
okay, sure. Okay, so thank you very much, Dr. Pui. So we end our section here. Okay, see you next time. Okay.
Okay, bye
Bye.
bye.